All right, so you can see my screen and hear me just fine?
Yeah.
All right, so today we get started with the day 7 slideshow. It's not finished yet because the material that I still need to include will be the stuff that I teach tomorrow. So I've included today's material in the slideshow, but I'm going to edit it tonight to include tomorrow's material. But it's still going to be on the same slideshow because it's kind of like the same topic. All right. So here are the topics of discussion. I wouldn't expect you to know what they are just yet, as always, but we're going to learn them. We're going to talk about implicit differentiation, higher order derivatives implicitly, calculus with inverses, the derivatives of inverse trigonometric functions, some useful inverse trigonometric identities, the derivatives of exponential functions, and the derivative of logarithmic functions. I don't think we'll get to the last two today.
Okay, gotcha.
So these are the topics that will be covered in the entire slideshow, including tomorrow. So we're going to work our way through the slideshow today, and whatever we don't finish today, we'll finish tomorrow.
Cool, sounds good.
All right, so implicit differentiation, I included this thing right here, but it's just like a process for how to do it. But before we understand the process to do, we actually have to understand what it is. So I'm just going to go into Jamboard and explain what implicit differentiation is, and also use Desmos to help me out, if that's all right with you.
Sounds good.
Cool. All right, so all right, let's start with the simple example of the unit circle, right? So remember we kind of introduced this topic yesterday, right? Where I graphed the unit circle on Desmos, and I said, is it a function? You guys said no. And I said, could we find the slope of the circle at a point? And you said yes, because if we zoom in far enough, it looks like a line. So we kind of have like two conflicting ideas here. On one hand, it seems like we could definitely calculate the slope of this relation. And remember, all a relation is an equation that relates two variables, and the graph that you get from that is the graph of the relation. Notice how relations don't have to be functions, because this is an equation that relates x and y. It doesn't produce a function. We call it a relation, and this is the graph of the relation.
Okay, that makes sense.
Cool. So we have conflicting ideas here. On one hand, it seems like we could definitely calculate the slope of this circle at any point, but on the other hand, it's not a function. So do our derivative rules work here?
No, I don't think they do.
Yeah, right now, the way we've defined them, they don't work. So we have to think of a clever way to try and figure out the slope of relations if we can't find the derivative explicitly. The kind of process we've been doing before this with functions, I would call it explicit differentiation. We're taking the derivative head on, right? We're using our derivative rules and just calculating the derivative.
Yeah.
Implicit differentiation kind of weaves around it, and we find the derivative implicitly by doing some process, which I'll explain in just a minute. So do you kind of see why this would be called implicit differentiation instead of explicit?
Yeah, that makes sense.
We're kind of finding the derivative implicitly.
Yeah,
all
that
right.
makes sense.
Cool. All right, I'll explain it. All right, so let's graph our unit circle. You know what? I won't even graph our unit circle. All right. You know our unit circle looks like this. It's just, actually, you know what? I will graph it just because.
Okay.
All right. It's a terrible drawing, but you get the idea, right? So here's our unit circle, and our unit circle is described by the equation x squared plus y squared equals 1.
Yeah.
Okay. And I'll reiterate to a topic that we discussed a couple classes ago. Do you remember the notation we did for derivatives, where we wrote derivatives like this? We imagined that the derivative is an operation you do on some function.
Yeah.
When I put the ddx here, it's an operation that I do to the function, and that operation is finding its derivative. Cool? So I'm going to do something weird, and I'll explain what I'm doing in just a second. All right? These two sides are equal. So if they're equal, I can do the same thing to each side, and it would be valid, right?
Yeah.
So I'm going to apply the operation ddx to both sides.
Oh, okay. Yeah, that makes sense.
And you'd agree that it's valid because we're doing the same thing to each side.
Yeah.
And it seems like we'd have no problems until we get to the y, right? We could take the derivative with respect to x of x squared, and we get 2x. We could take the derivative with respect to x of y squared, and then we're like, we have a problem here. How do we do that?
Yeah.
All right, so we're going to skip that for now. And we'd say that's equal to the derivative with respect to x of 1, which is, do you remember what the rule is?
It's 0. It's just
Exactly.
a straight line.
So this seems like a viable method, but the only problem is we don't know how to deal with this y term. How do we find the derivative of this when, can you see that this is a function with respect to y?
Yeah.
I'll explain what I mean. You can imagine that we're graphing y squared where our inputs are y. So y squared is a function of y.
Okay, yeah.
Right? It's not a function of x. So we seem kind of screwed here, right?
Yeah.
But, do you remember with the chain rule? We found the derivative of something with respect to x when the function f has inputs, let me rewrite this. When the function f has inputs of g of x and not x.
Yeah.
Right? So in the chain rule example, we perfectly found the derivative of f of g of x with respect to x, even though f was graphed with g of x as inputs and not x. So the same idea kind of follows, right? Even though the graph of y squared, right, is a function of y, all right, we can still kind of use the idea of the chain rule to find the derivative of y squared with respect to x, because with the same kind of logic. Here we're finding the derivative with respect to x, even though the function does not have x as inputs. We're going to do a similar process here. So I'll explain more in depth in the next slide. So even though y is not written as a function of x, all right, I think you'd agree with me that the value of y still depends on the value of x.
Yeah, definitely.
Even though they're not functions, they depend on each other. All right? So because y and x still have this relationship, we can still take the derivative of y with respect to x because they're still related to each other in this manner. They still depend on each other. So if I asked, what's the derivative with respect to x of y squared, right? Let's look at Leibniz notation. Leibniz notation tells us that if we want to do the chain rule, right, we take the derivative of y with respect to some other function times the derivative of y with respect to x. Right? Remember Leibniz notation?
Yeah, I thought the other side.
Oh, yeah, my bad.
Yeah, okay, cool.
Good. I was totally testing you. Didn't make a mistake.
No, I know you would never do that.
Yeah. So this is Leibniz notation. All right.
Okay.
So we can use the chain rule here to try and extrapolate the derivative of this with respect to x. All right. So we're trying to find the derivative of y squared with respect to x, right?
Yeah.
And the reason that we can do this is because even though y is not a function of x, y still depends on x. So we could still find the slope of this with respect to x. They're still dependent on each other.
Okay.
Cool. So this tells us that if I want to take the derivative of a function with respect to x, I could take the derivative of the original function with respect to some other function. So I'm going to say dy. I'm going to take the function that I'm considering. I'm going to say that I'm taking the derivative of y squared with respect to y.
And then are you going to find...
And then I multiply that by dy over dx.
y of d of x, yeah, okay.
So I found the derivative of y squared with respect to x is the derivative of y squared with respect to y times the derivative of y with respect to x. That's just the chain rule.
Yeah.
Does that make sense?
That makes perfect sense to me.
Cool, awesome. So the derivative of y squared with respect to y, could you guess what that would be?
2y?
Exactly. So if I took the derivative...
it would just be the same rules, it's just a different letter, right?
Exactly. So we're all implicit differentiation is the chain rule. That's all it is. It's just an application of the chain rule. We're saying if we want to find the derivative with respect to x of y squared, we just use the chain rule. We take the derivative of y squared with respect to y, and then multiply it by the derivative of y with respect to x. That's the chain rule.
Perfect. Beautiful.
So let's go back to our original example. we'd have d dx, x squared plus y squared equals d dx1, right? So we'd get the derivative, so we do the sum rule, right? So the derivative of the first one is just 2x. And the derivative of the second one we said was 2y times dy over dx. Right? You follow me on that?
Say it one more time.
And the derivative of the second one is 2y times dy over dx, because that's what we said before, remember?
Yeah.
Okay, cool. And that equals the derivative with respect to x of 1, which is 0.
Okay.
Now I can do some algebra. I'll take 2y is equal to negative 2x, or 2y times, let me backtrack. 2y times dy over dx equals negative 2x, just from subtracting 2x from both sides.
Yep.
All right, I'm going to divide both sides by 2y. dy over dx equals negative 2x over 2y. The 2's go away. And dy over dx equals negative x over y. And what does dy dx mean? Does it tell us the slope at a certain point?
Yeah.
Exactly.
It's negative x over y.
Exactly. So if I wanted to find the slope of the circle at some point, I would take the negative x coordinate and divide it by the y coordinate. And we just showed the process for doing that and why it works.
Okay, cool. So then you can use this formula for, like, to find...
Yeah.
Can you use it for other relations?
Yeah,
like,
you can do it. This idea works for any relation.
Word.
Cool. So if I wanted to find, for example, x squared plus y squared plus 9xy equals 0, I would do the same process, all right? I would take the derivative of both sides with respect to x, because we can do that to both sides. If I take the derivative of this thing with respect to x, I'll get 2x plus 2y dy over dx, and then plus the derivative of this, all right? And we can use the same process to find the derivative of this. Would you agree that this is just 9x times y?
Yeah.
So we're going to end up using the product rule. The derivative with respect to x of this is we can find it using the product rule. So we get 9 times y plus the derivative of y with respect to x, dy over x dx, right? That's just the product rule, times 9x.
Yep.
So do you see how this is the derivative with respect to x of 9xy?
Yeah, I do.
Cool. So then what we do is we rearrange our equation to get our dx on one side, and we get a formula for what the slope is. Because dy over dx, by definition, is our slope at a certain point.
Yeah, okay.
So all implicit differentiation is using the chain rule when we get y's, right? The way we differentiate y's with respect to x is we just use the chain rule. If we have a y squared, we know we can differentiate y squared with respect to y. That's just 2y, all right? And then the chain rule tells us we then have to multiply it by the derivative of y with respect to x. And the cool thing is, when we do this process, we get these dy dx's, which we know is the slope. We know that represents the slope of our line, or the slope of our function, or not function, our relation. So that's why this process works. By virtue of taking the derivative of y, of things that are y, we get these dy dx's terms, right?
Yep.
And here's a little cool example. We've technically been doing implicit differentiation this whole time. All right, let's look at y equals x squared. I could take the derivative of this by just doing by taking the derivative with respect to x of both sides, right? So you'd agree the derivative of y with respect to x is just dy over dx, right?
Yep.
And then that equals the derivative with respect to x of x squared. Do you see how this is the exact same formula we got when we calculated derivatives explicitly?
Okay, yeah, that makes sense.
So we see that implicit differentiation also matches what we would expect to get by doing explicit differentiation.
Yeah, okay, that makes sense.
Awesome. So what I need you comfortable with is the idea of implicit differentiation. You have an equation. You can do the same thing to both sides. So we call it applying. This is a fancy math word, and you can sound really cool when you say this. You can say, we apply the derivative operator to both sides.
Ooh, okay.
We apply the derivative operator with respect to x on both sides.
Okay.
That's the fancy way to say it. So you can go like, yeah, you can go to your friends and go like, yeah, I know how to calculate I know how to apply the derivative operator with respect to x to both sides of a relation.
Yeah, so like this morning I was just busy like using the derivative operator.
Yeah.
They'll just like.
Yeah. Be careful though. If there's any women around, they'll probably want to take you home, and it might be a lot. So just be careful.
Okay. Thanks for the warning.
Yeah. Yeah. My experience is that math is really what gets women going. It's just math. It's all math.
I mean, you got a girlfriend, so like I know.
Fun fact. That's no longer the case.
What? You guys broke up?
Yeah. It's because I can talk about it later. The only problem is I won't explain it now because I'm recording it for YouTube. This is going on YouTube.
Oh yeah, I forgot about that. Okay,
but yeah, long story short.
Talk about it another time if you want to.
Yeah, no, yeah. I'm bottom line is I'm doing good. So
yeah. So glad to hear that.
Good. Awesome. So I need you comfortable with the idea of implicit differentiation. We apply the derivative operator to both sides because we can do the same thing to each side, and that's valid. And then when we get y's, we just use the chain rule to find the derivative of some y thing with respect to x. We just use the chain rule.
Yeah, perfect.
Awesome. And then once we finish with that, we try and get our dy dx's on one side, and then we'll get dy dx equals something, and that will be what we want. It'll tell us our slope is equal to something else, and that's what we want.
Okay. Yep.
And normally you'll notice, like with our circle, our slope depends on the x and the y coordinate. Like we had negative x over y.
Yeah.
That makes sense, right? Because in a relation, you'll notice the slope does not just depend on the x value, because at x equals 1/2, the slope down here is positive, but the slope up here is negative. So it makes sense that the slope would depend not just on x, but also on y.
Absolutely.
Cool. So I hope all of this is coming together and making sense.
This is all making sense. Yeah.
Awesome. Good. So implicit differentiation is, in my opinion, one of the most useful tools in calculus. So if you understand that, you're doing really good.
Yeah, I think I'm understanding it for the most part. It will also just kind of like come more as we keep talking about it. And
yeah, exactly. Good. And if we need to go back and emphasize a few points, we can. Implicit was a topic that took me months to understand. It took, like, I kid you not, it took me months to understand the heart of what was going on.
Yeah, okay.
So the fact that you already feel pretty good with that on the first day, I'm fine with that. And we're going to keep using it, and we're
only get stronger from here.
Exactly. And we'll keep coming back to it. We can do some practice problems, etc.
Okay, cool.
All right. So the next idea is taking higher order derivatives implicitly. And before I talk about higher order derivatives implicitly, I kind of just want to preview what a higher order derivative represents. Because remember we talked about higher order derivatives where you said, like, well, if we had x squared, we take the first derivative is 2x. Then the second derivative is 2 because we're taking the derivative of the first function.
Yep.
So we can see the representation of the derivative, the first derivative, in the graph of x squared, right? The first derivative will tell us the slope of the function, of the original function.
Yeah.
But we don't know how the second derivative shows itself in the first function. Like, what does the second derivative represent in the first function? We don't know that yet.
Okay, yeah.
And we're going to learn it in Unit 4, but I'll preview it now. You'd agree that the second derivative tells us how much or how fast the slope is changing, right?
Yeah. I think that makes sense to me because I think using the application of like speed.
Yeah.
So then it's like.
Exactly.
Like if the speed or if the distance
Yep.
relative to time is changing at a rate of x squared.
Yep.
That means that the the velocity is 2x, and then the acceleration, which is the rate of change of velocity, is 2.
Exactly. So this is just that exact definition, just applied generally to graphs and functions.
Perfect.
So the second derivative will just be how quickly the first derivative is changing. So if we look at our first, so let's look at the graph of x squared where our second derivative is 2. Our second derivative tells us how quickly our slope is changing.
Yeah.
Right? So let's say we had a function that looked like this. All right? Wouldn't you agree that the slope changes, the slope is here and then it changes really quickly, right?
Yeah.
So the second derivative here is big because the slope is changing quickly.
Yeah.
All right? Additionally, the second derivative of this function, right, would be small because the slope is not changing quickly at all. It's changing very gradually. But this function, the slope is changing very quickly.
Yep.
So the graphical representation of the second derivative is basically the curviness of the function. It's how curvy it is. And it's because if our second derivative is high, our function is going to curve up much quicker because the slope is changing very quickly. But if our second derivative is low, then the function is going to curve upwards very slowly because the slope is not changing very quickly.
Yeah.
Okay. Cool. So the graphical representation of the second derivative is how curvy the function is.
That makes perfect sense.
Okay, cool. So naturally, it seems useful to try and find the second derivative of implicit functions because obviously you can see, well, the function's curvy, right?
Yeah.
So we could find the second derivative. So finding the second derivative of this relation might be a useful thing to do. All right. And how we do that is we do it in the following way. Remember in the circle, we got dy over dx equals negative x over y. Remember that? So if I want to find the second derivative, I can just apply the derivative operator to both sides again. And would you agree if I take the derivative of respect to x of the derivative of y with respect to x, I'm getting the second derivative?
Yeah.
Cool. Does that make sense, or you want to take a second to let that sink in?
I think that makes sense. And the more we talk about it, the more.
It's just we're asking the rate of change of dy dx when we apply.
It's like what's the even if you say it as the derivative operator, if that's what that means, I think it's fine. But it's like find the derivative of the derivative.
Exactly. Find the derivative of the derivative. That's the second derivative.
Yep.
Cool. So the second derivative will be the derivative of this. All right. And we can use the quotient rule. All right. So the quotient rule tells us the derivative of a quotient is going to be the derivative of the top one, which is 1, negative 1, times the bottom function, all right, minus the derivative of the bottom function with respect to x. So the derivative of y with respect to x, I think you'd agree, is dy over dx.
Yep.
Right? Times just the top function, negative x, over the bottom function squared.
Okay, yeah.
And so the second derivative is equal to this. The only thing is we have a dy dx in here. But we know from the first equation that dy dx equals this, right?
Yeah.
So I'm just going to replace dy dx with negative x over y. And boom, I have a second derivative entirely in terms of y's and x's.
Nice.
So do you see the process for finding the second derivative? It's the same process, but whenever you get dy dx's, you replace it with what you got in the first derivative.
Okay, yeah, I think that makes sense. Real quick, how on the left, how did you get to dy squared over dx?
Sorry. Let me go back. Sorry. I wrote the notation wrong. It's this very simple answer.
Oh, word.
What I meant to write is the notation we're all familiar with, which is d squared y over dx squared. Do you remember we said this notation represents the second derivative?
Yeah. Okay.
I meant to write that.
then that makes perfect sense.
And also, you can see why we use this notation, right? Because when we take the derivative of this, we write this because we could imagine the d's multiply together, right? So we get d squared y, and the dx's multiply together to get dx squared. That's not really what's happening, right? We're not multiplying two things together. We're doing an operation.
Yeah, because d isn't like a number.
Exactly. But if you're wondering why we write it like this, that's why. It's like we're not multiplying them together, but if we were, that's what it would look like. So we just write it like that.
Okay. Yeah. No, that makes sense.
Okay. All right. So what I need you comfortable with is at least kind of the idea of implicit differentiation and the idea of higher order derivatives using implicit differentiation. Because we could do the same process, right? We could take the derivative of the second derivative and get the third derivative, right? So we could keep doing this process to find all the higher order derivatives we want of a relation. Okay? Any questions before we go on?
I think I'm all set.
All right. Now that we have the useful tool of implicit differentiation under our belt, finding the derivative of inverse trig functions becomes something we can do. But before we get into that, let's make sure we're all on the same page. I think the next page talks about it kind of goes in deeper to what I was saying earlier. All right. So far, we have only discussed derivatives with respect to inputs of our functions, right? So like d over dx, d over dt, whatever our variable or input is. And this tells us the slope of the function. What if we flipped our coordinate system on its side? We're going to turn our world upside down figuratively. All right. Let's say that we graphed, this is our x-axis and this is our y-axis. All right. And we graphed x squared. This is our x-axis in the positive direction, and this is our y-axis in the positive direction. Down here is the negative direction for y, and over here is the negative direction for x. Right?
Yeah.
So what if I flipped it on its side so the y was the x-axis and the x was the y-axis? We'd end up getting this. So I'm basically flipping this 90 degrees this way. All right? So I get the positive y direction this way, the positive x direction this way, the negative y direction this way, and the negative x direction this way.
Interesting. Okay.
All right. So you'll notice it looks like our original thing. The only difference is because we've rotated it, the y value, the positive y values are in the other direction. All right. So if we look at our graph of x squared, we can regraph it on our new rotated thing, and it looks like this, right?
Yeah.
Cool. So if I asked you to find the derivative with respect to y of this, right? Wouldn't you agree that just asked me the slope of this at some value y?
Yeah.
And do you notice how the slope with respect to y is different than the slope with respect to x? Here's the slope with respect to y. It's negative, it's positive. It sounds weird that it's positive, but remember that the positive y direction is to the left this time. So even though this looks like a negative slope, because our positive directions are switched, this is a positive slope.
Okay.
All right. So here's the slope of our function if we look at it from y's perspective. Wrong thing. But here's the derivative of our function if we look at it from x's perspective. And can you notice that the derivative with respect to x is steeper?
Yeah.
Cool. So basically, we get different things depending on what we're differentiating with respect to. And the idea of differentiating with respect to x, d over dy, is doing this, all right? We take our function and we imagine that we're finding the slope if we were looking at it from y's perspective. Which means we rotate our graph so that the y is where the inputs would be. And we take this and we flip it on its side like this, all right? And when we find d over dy, we're finding the slope of x, because x is our new height, with respect to y.
Okay, yeah.
We call this dx over dy.
Cool.
All right. So taking the derivative with respect to y of something, that's all it means. We're asking, what does the slope look like if we look at it from y's perspective? Does that kind of make sense?
Yeah, that makes sense.
Cool. All right, so if I were to graph x equals y squared, not y equals x squared, but x equals y squared. From x's perspective, it looked like this, right?
Yeah.
But from y's perspective, it looked exactly. So remember, from our y's perspective, the positive y direction is switched because when we flip it over, that's what happens.
Yeah.
When we look at it from y's perspective, the graph looks exactly the same. All right.
Yeah. Okay.
As x y equals x squared, because it's x equals y squared. So if I took the derivative of y squared with respect to y, it's just 2y.
Yeah, because that's the same thing as d of x squared.
Yep.
Yeah.
Exactly. So I just want you to comfortable with the idea of taking the derivative with respect to y. It's basically asking, what does the slope look like from y's perspective?
Okay. Yeah, that makes sense.
Cool. That's why we use the with respect to, because the with respect to tells us whose perspective are we looking at it from.
Okay, that helps. Yeah, okay. Yeah, that makes sense.
The derivative with respect to x is like we're asking what does the slope look like to x. The derivative with respect to y, what does the derivative look like to y?
Okay, cool. Yeah, that's a good way of putting it.
Yeah, cool, awesome. I'm glad that makes sense. All right, so this just goes over what I explained, and we're going to read it and make sure that we're all familiar with it. And I don't know if our meeting is going to time out at any point, but if it does, we'll just come back and we can figure out what to do.
Okay, it says we have 7 minutes left.
Okay, I can get through a couple more things. All right. What if we flipped our coordinate system on its side? So the y-axis became the x-axis and the x-axis became the y-axis. That's what we did. Each point now looks like it has a different slope with respect to y. That's what we said. If we look at it from y's perspective, each point has a different slope.
Yep.
If you wish to find this new slope, we can take the derivative of our function with respect to y. That's what we're saying. If we want to find the new slope, we take the derivative with respect to y, because that tells us what does the slope look like to y. I hope that's self-explanatory.
Yeah.
Yep. All right. So this will tell us what our slope looks like in our sideways world. The bottom line is you can take the derivative of something with respect to an input, an output, or whatever. You can take the derivative with respect to anything. Because all you're asking is, what does the slope look like from this thing's perspective?
Okay. Yeah, that makes sense.
So that also goes back to taking the derivative with respect to g of x. We're asking, what does it look like from g of x's perspective?
Yeah.
We could also make g of x our inputs. The bottom line is we can take the derivative with respect to anything, and we're just asking, what does the slope look like to this thing?
That makes sense. Okay, I definitely follow that.
Cool. All right. This is what we talked about before. So the idea of taking the derivative of f with respect to g of x, that's exactly this. We're saying the same thing, right? If we graphed f of g of x with respect to g of x, so g of x are our inputs, and we calculate the slope, we're going to get the derivative of f of g of x with respect to g of x, right? Because they ask us, what does the slope look like to g of x? And g of x is our inputs.
Yeah.
So that just goes back to the idea of taking the derivative with respect to g of x.
Okay.
This slide just goes with what we talked about with the chain rule. So I think we can skip it. We already talked about this.
Yeah, cool.
Okay. All right. Let's make sure we're all on the same page with inverse functions. Remember, inverses are functions that undo each other. If we go to our machines, we can see this very clearly. All right. Remember, we said inverse functions, if f and g are inverses, all right, then if we stick in x and put it into the function g, we'll get out g of x. And if we put g of x into f, it'll spit out x again. Inverses are functions that undo each other.
Yep.
Do you remember that definition from before?
I think, yeah.
Yep. So our function f is taking g of x as inputs and spitting out x, whereas G is taking in an x and spitting out g of x.
Okay, yeah.
All right. So these are basically they're the exact same functions but opposites of each other. For f, g of x is the inputs and x is the outputs. So we could graph the function f by just taking the input-output pairs of the function g, right, and reversing them.
Yeah.
Because, the inputs to f are g of x and the outputs are x. So if we just take the input-output pairs of g and switch them, we'll get the graph of our function f.
Okay, yeah.
Does that make sense?
I think so, yeah.
Yeah, all it is that f is taking g of x as inputs, so our x coordinates are g of x, and its outputs are x, so our y coordinates are x.
Okay. Yeah, no, that actually makes a lot of sense.
Okay.
I understand that.
Okay, cool. So when we do the algebra trick where we say if we want to find the inverse function of this, the reason the algebra trick of switching the variables works is for that exact reason. You might have learned this in pre-calculus. When you're finding inverses, you just switch the variables.
Yeah, I think I did.
All right? That's the reason why. From what we just explained. All right?
Yeah.
Cool. All right. So this is saying what I just said, and after this, we'll end the meeting and we'll come back because I think we're going to end very shortly.
All right. Yeah, cool. Sounds good.
Okay. Remember, inverses are functions that undo each other. If we go to our machines, it's clear that an inverse function takes the outputs of the original function and spits out its inputs. This means that if we graph the graph of if we want to graph the inverse function, we just graph the original function's input-output pairs in the opposite order. That's what we just said in a complicated way. In other words, a normal function would have points x, f of x, where x is the x coordinate and the output is the y coordinate. But inverses have coordinates f of x is the input and x is the output.
Okay.
All right. So so using that, we can find the graph of the inverse of any function just by taking every single point and switching its order. Does that make sense?
Yeah.
Okay, cool. All right. This next part we can get to after we end the meeting, so I can get a fresh start.
Okay, cool.
Why don't we... Here's what I want to do. Well, I want to finish this slide. We might hold off inverse trig derivatives until next time.
Okay. Yeah, whatever you decide.
All right, and if you want to do more, we can do that. But I also understand that we've learned a lot today, so it might be a good idea to do these last two slides.
I'm kind of with that. I think maybe like a little bit of a break, just like pace ourselves.
Yeah. So do you want to take a break now, or do you want to just get through these last two slides and call it a day?
I'm happy to just keep going.
All right. So